Good morning, everyone.
Good morning, Dick.
I'm Dick Cole. I'm a member of your Let's Talk Science Committee. And our speaker today is Dr. Edward Baker. He's now retired from the University of Washington. And
We can't hear you.
You can't hear me. Now you can. And we can also thank fellow resident Kathy Cullen for suggesting that Dr. Baker join us. She thought he would provide an interesting and stimulating talk about a subject most of us know absolutely nothing about. Dr. Baker came to Seattle in 1967 to attend graduate school at the university, and he never left. After earning his PhD from the U in 1975, he worked until 2013 for NOAA's Pacific Marine Environmental Laboratory in Seattle. He then returned to the university as a research fellow until 2019, where his field of specialization was, are you ready for this? Hydrothermal systems powered by seafloor volcanic eruptions and their effect on the deep ocean. I'll repeat that. Hydrothermal systems powered by seafloor volcanic eruptions and their effect on the deep ocean. Dr. Baker's research has taken him on more than 80 cruises along oceanic ridges and volcanic island groupings throughout the Pacific and Southern Oceans, as well as the Mediterranean Sea. He's published more than 250 technical papers, has received a Distinguished Career Award from NOAA, and is a Fellow of the American Geophysical Union. Let's give Dr. Baker a warm welcome as he tells us what he's seen, where the water is both very deep and very warm, and tell us what's down there, Ed.
Okay. And I presume you can hear me as well? Is that good? Okay. Thanks, and thank you for the introduction, Dick. This talk is about volcanoes and life. If some of you came thinking this was a therapy talk on how to make your life richer and fuller using volcanoes, this is not it. You're welcome to stay, and maybe your life will be richer and fuller for an hour. Okay? So, those of us who live in the Pacific Northwest, particularly if you go to Hawaii once in a while, we're more familiar with volcanoes than most of the people in the country. We cruise down I-5, past this majestic chain of volcanoes. Baker, people often say that's the most majestic. Rainier, Hood, Adams, St. Helens, Shasta, many others. What goes through your mind when you drive by these geologic giants? Grandeur? Sure. Destruction? Maybe. Death? It was only 43 years ago yesterday Mount St. Helens went off, the latest volcano in the Cascades. But I'm going to tell you that 80% of the volcanic activity on the planet occurs out of sight on the seafloor. 80%. Those volcanoes have some amazing differences from the volcanoes we can see, and some familiar similarities. This is an underwater eruption on the screen in the deep sea, but it could be a lava flow in Hawaii easily. So I'm going to break this talk into 4 sections so it's easier to follow. First, a very simple question. Why does the Earth have volcanoes? And what's their distribution? The west coast of all the Americas is full of volcanoes. The rest of those continents, not so much. Then we'll go down and look at some seafloor volcanoes. We'll look at equipment and how seafloor volcanoes are studied. And then I'll show you some videos I'm pretty sure most of you have not seen before. Most people have not. Some amazing activity on the seafloor. Then the main topic, volcanoes and life. Volcanoes aren't just destructive, but you'll see they may well be essential for life. And finally, what can they tell us about life beyond Earth? Always an interesting question. All right, let's get going. Why volcanoes? This is what most people think about when they say the planet Earth, the water planet, where the early astronauts called it the big blue marble. It has the largest store of liquid water in the solar system, as far as we know, and I can't imagine it would be elsewhere. It makes it unique in the solar system. Earth is also unique for another reason. It's the only dynamic planet. All the other planets and moons have solid crust that don't move. Earth is the only one with various tectonic plates. These are 12 of them here. We have one little one right off our coast. There's probably another 2 or 3 small plates, dozen plates, but these are the principal plates. You know they match up with oceans and continents pretty well. It's just a little clearer, I think, if we look at it this way. The white lines are places on Earth where plates are divergent. They're moving apart from each other, and new magma is coming up between them. That means those white lines, which occur, trying to get the pointer up, all over the globe pretty much. There's 40,000 miles of an active volcano. Those lines are active commonly. Now, the Earth is not getting any bigger, so where do the plates go? That is subduction zones convergent where the plates are consumed. You can see these black lines, they circle the Pacific Ocean, and there's another black line through Asia and Africa, noting where these plates here, the big continents, are moving into Asia. So those are the boundaries of the plates that make up our planet. Continents have rocks as old as 4 billion years, but the oldest rocks in the ocean are only about 200 million years, because the ocean crust is continually recycled, whereas the land, the cratons, the granite crust of the continents are light enough that they just float on top. So this is an interesting connection between subduction zones in black and earthquakes. You see there's an almost perfect matchup, because that's where the various plates are running into one another, and there's plenty of volcano eruptions. Earthquakes up in Alaska in '62, all through Chile, the big one in Japan 10 years or so ago, the recent one in Turkey, the big tsunami that was in Thailand. That's where all those big earthquakes occur, and that's because of those moving plates. All right, let's take a closer look at our plate, the Huatantuca plate, and plate creation is occurring there. You can see as the Pacific plate moves west, the Huatantuca plate moves east. And as they separate, magma comes in to fill the crack. The magma is not pushing the plates. You can't do that. You might get a big rug at home, you try to push it across the floor, It doesn't work. You just can't push an unsolid plate. We'll get to that later, but so that's the divergent plate boundary, and we'll look at this in a little more detail, cross-section right across here. All right, this is what they look like on the seafloor. This is where the plates are separating. Ridges separated about 1 to 6 inches per year, about as fast as your fingernails grow. When they're a slow ridge and only separated at 1 inch per year, this axial valley can be up to 10 miles wide and a mile deep. On a fast ridge, it might only be a few hundred yards and tens of feet, but it's still the same principle. Because these plates are under tension from moving, the rocks are all cracked. That means seawater can percolate down to the rock, get heated by the magma, come up in a buoyant way, about 600 or 700 degrees Fahrenheit, and gush or leak out of the seafloor. If it gushes, if there's no impetus, it looks like a geyser or a stream. Much of the water, though, gets mixed with seawater as it kind of leaks out around the edges. As this goes up into the water, it forms a plume, which carries lots of stuff into the ocean. It rises a few hundred feet or several hundred feet. Lots of metals, and most importantly, I'm going to be talking about these two a lot in the talk, CO2 and H2S. Now, has anybody ever walked along one of these axial valleys? I bet some of you have. Does this look familiar? It's Iceland.
Oh.
And in Iceland, the ridge is high enough, it comes above the sea level because of the hot spot underneath it. And Iceland is being pulled apart by plate separation. And you can go to Iceland and walk through an axial valley where the plates are spreading. The spreading part is actually about several miles across. This is just one fracture of that. You can go there and say you've walked across the mid-ocean ridge. All right, let's look quickly at plate consumption. Here's where the Juan de Fuca plate is coming down, and it's going under the North American plate. Many of you may have heard of the Cascadia Fault. This is where the Cascadia Fault is, and that's where the tsunami-producing earthquakes happen. I can tell you with some precision that this fault will fail somewhere between 5 minutes and 500 years from now. That's not the best we can do. So let's look at that a little more. Well, what happens is this plate begins to melt a little bit and release some magma, and that magma moves through the North American plate and comes out as volcanoes that we see around Seattle. So it looks the same thing as the other picture. This is a subaerial volcano. There's also volcanoes underwater, same thing. But water gets in, gets heated, moves out in a plume, and those same chemicals are given off. Now, I'm sure somebody will think about the fact that they've seen this in operation around Seattle, right? Does that look familiar? Mount St. Helens, after the eruption, and Mount St. Helens is now producing a new lava dome, beginning to build back up. That water that gets heated from snow inside the lava goes up several hundred feet, reaches a buoyancy level, and then it gets floated across our city, our area. So it looks exactly like what's going on underwater. Okay. It might help to look at this, which is this is the Juan de Fuca plate. This is very old bathymetry, like 20 years old bathymetry. This video was made a while ago. So this looks a little smooth, because we didn't have good equipment then, but you still get the same effect. You can see this is the Juan de Fuca ridge that I've just been talking about, the Cascadia Fault lies over here. And there's a small hot spot here which intercepts the ridge, kind of like Hawaii. So we're flying along the ridge here, and you can see those stripes on either side of the ridge representing different episodes of spreading of new magma coming in as the plates spread apart. It isn't a continuous process. The plate never stops moving, but the interval in which magma is added changes from century to 1,000 years. So we'll just move along here quickly. This has more magma being fed to it right now than this sediment right next to it, which is much deeper and farther apart. And then it runs into what's called axial volcano. It's about 3,000 feet above the seafloor, and it has on the top of it a caldera, much as Kilauea does in Hawaii. And then the ridge just keeps going. Lots of little volcanoes by blobs of magma that are forced up to the mantle in this whole part, this whole ongoing process. Here's another ridge crest, which is very high. And then one final little feature, the ridge jump, it moves from time to time a little bit, and then it intercepted an existing volcano and cut it right in half. So the spreading ridge is right here, and this is an existing volcano. Okay, so how do we find these vents on the seafloor since they're not very big? Originally, people would go down with cameras or a submersible and drive around and try to find something, but that didn't work very well. So our group back in the 80s developed this technique where we tow sensors from a ship, drive along at about a mile an hour over the water, and then we tow the sensors in this sort of up and down fashion for several hundred feet up and down near the seafloor. And as you can see, here's the vent right here, a very small thing, a very small piece, but it makes a big plume, just like I showed you in Mount St. Helens. And the sensors can paint a picture of where the plume is, so then submarine or other sampling can come right back to this area and find the vent. So this technique really revolutionized the discovery of plates, or vent fields, all throughout the world's oceans. This is how many vent sites on the ocean floor that we know of a few years ago, about 600 or so. Half of which were confirmed because someone took a picture or someone saw it, and the other half is just inferred by that plume evidence I just described. We think there's one. Now you may think, oh, there's a lot here and none here. This map shows precisely where ships have been and where they have not. If ships come here, they'll find a lot of vents. They'll find a lot of vents. So this is just the state of exploration. It's really hard to explore down here in bad weather. Up here, it's nice and warm, and up here, it's near nice ports, and here there's a lot of people. So there's vents, there's probably thousands of vents on the seafloor. All right, exploring the seafloor. How do we do that? Okay, back in the 60s, Woods Hole developed a submarine, human-occupied vehicle called Alvin. It was designed to go down to at least 12,000 feet. It had a 6-inch, it felt like 6 inches, 6-foot diameter titanium sphere with 3 portholes. It held a pilot and 2 observers, 2 scientists. You get in the submarine after breakfast. You sink down, took them an hour or 2, depending on how deep you were going. You spend 4 or 5 hours on the seafloor. You dropped a bunch of little weights, and you floated up in time for dinner. So that's a great idea, but in the end, you're only up there in the seafloor for 4 or 5 hours. Not much time, and there's only 2 of you. But it is a lot of fun, as this guy can tell you. So this gives you an idea of what it's like down there. Here's a little porthole right here, and you're pretty much encased in gear, and 2 other people that was it. So it was an experience of a lifetime, though, the amount of times I did it. Now, just as in space exploration, people not figured out, but you can see now the space station is great, but it's very expensive because there's humans, and satellites do a much better job of exploring the solar system than man does so far. So the same thing in oceanography. People started making remotely operated vehicles tethered to the ship, so they can't go too far, but a lot of complex machinery, a lot of sampling, a lot of mapping, and it would work for 1 or 2 or 3 days perhaps, and everybody on board could see what was happening. This is me just looking at a small piece of my own data coming up, but actually this is what's controlling. So it's much more crowded and active, and kind of a mini Houston control center. But that really changed things. People still use submersibles, but not nearly so much. And finally, we all know about drones. Well, I'm sorry. Spit ahead here. This is what the ROVs can do. This is an ongoing eruption at the seafloor. You can see the clouds of steam, and see the yellow there? That's hydrogen sulfide, sulfur particles now. This is ash from being blown up into the water and pummeling down. Here's the gear of the ROV, and there's a pipe in here trying to get some samples of the gases that are coming out of the volcano. And you see all the bubbles in the CO2. Remember I mentioned CO2 is a big deal? Volcanoes put out a lot of CO2. So this is another reason you cannot do this with a human-occupied vehicle. All right, finally, drones. Drones are big everywhere now, and there are 2 in oceanography. You just set a drone in the water, and it will run a predetermined path. I'm not sure they have sampling capability. If they do, there's not very much, but they take a lot of data. They make a lot of very good maps, and they take great pictures. And this shows a picture. We had found some plumes in the Mariana Trench at about 14,000 feet. And because of the chemistry of the plumes we found, we suspected there was an eruption recently. So we sent the sentry down to make maps, and this is one of the pictures they found. This is lava that's hundreds to thousands of years old, covered with a lot of sediment. Here's brand new lava, meaning months to years. So this is clearly very close to where the eruption site is. So now we know more precisely where to put an ROV or a submersible down to do the work, rather than just driving around hoping for things to go better. All right, now let's do some fun stuff. Okay, high temperature events, smokers. I told you about the black smoke that was going to be coming out of this. This is the Mariana Trench, about 11,000 feet. So all these chimneys are where the metal precipitates at metals, where the metals have precipitated and built these chimneys. And you can see what the smoke looks like. It's jet black and it's coming out from a great number of places. There's a close-up of it. That's the fluids that are coming out are 600 or 700 degrees Fahrenheit. Well, you can see the animals living right next door, because the moment that really hot water gets in the ocean is an enormous heat sink. It cools down dramatically within a second or two. So the animals can get pretty close. There's a lot of familiar crab-like animals, shrimps. Here's another orifice here, the chimney coming out. And these things, I don't know exactly how high this is, but it's maybe 100 feet tall, which is a remarkably big one. Okay, here's a really spectacular one. There you go. You've got some audio. This was down near the Fiji area. We're at 4,000 feet deep, and this is an erupting volcano. And we're really fortunate not to be in a submarine, but we're fortunate to be there with an ROV, and you can see there's so much gas coming out of this volcano as it erupts that it makes these bubbles. And if you freeze frame these, they look like a glass float, just for an instant, until they explode apart. And you can just see all this ash is very fragile. The eruption is still occurring. Stuff is tumbling downhill. There goes another pop. And if you look carefully, you'll probably see some yellow in these clouds, showing the presence of sulfur, which is always there, plus carbon dioxide. And you can see here we are, the ROV very close. Everything survived well. And this was a really big deal. Nobody had ever seen anything like this. This was maybe 10 years ago that we filmed this. There's a good one. I don't think anybody ever imagined they could get bubbles like that almost a mile down in the ocean.
What's the pressure down there?
It's 400 atmospheres. It's a lot. I don't know what the PSI is, but it's a lot. All right. There we go. All right, speaking of bubbles, not these bubbles. Oh, I'm sorry. We're going to go to the diffuse fluids first. So this is a very different picture. This is a hydrothermal vent also, but this is a diffuse vent where the temperatures are very low and the animals can easily live. These are the iconic vent animals called tube worms. You find them everywhere. Watch this one right over here on the far right, for those of you looking at the screen. The far right, and that crab is, I think he just forced one of those. Oh, there we go. So he just got it poking around, and that worm brought in its tube. These are tubes that the worm uses to collect hydrothermal fluids and feed itself. And I'll go into that biology thing a little bit more later. But these are really what people think of as the most unique. Well, the only place they're found on the planet is by hydrothermal vents. And they're very beautiful and spectacular. And here's a crab trying to get down on the left-hand side, trying to get down inside a tube and get at the meat of the worm. Here's a little different view. This looks like a whole field full of things you could walk down to Ivor's and have for lunch. Although there'd be a kind of a bad aftertaste. I'm sure you're right. The way they're aligned is that tells you really where the cracks are that the hot water is coming out. Doesn't that look like something on the menu? That was tribes, but it's really a rich ecosystem down there. Let's look at a couple other. There we go. These are mollusks. And you can see the waving water all around that. That tells you the water is being diffracted because of the hot water. The light is being diffracted through this hot water. It's coming out pretty hard. Here's some more shrimp. They're always around because they are grazing like cows, on the microbiology that lives on these structures. They just wade along eating the microbes, and that's the start of the food chain that prevents this. And then fish come in to have themselves in it as well. Now here, brings me to Thomas Hobbes, I think, famous statement that life is brutish, beautiful and short. Vastly brutish and short life is. You can see here the crabs and the mollusks are really, well, there's an advancing army of crabs trying to have a meal with all these mollusks, and they're desperately trying to avoid, but you can see the frenzy that's going on. But this is the only food around for quite a ways. Okay, this is something that no one ever expected to see.
Look at this stuff. Oh my God! This whole lake is undulating.
Yes, gas coming up through the sulfur. Black, though.
Oh yeah. Black, that's what confused me at first. The whole thing's moving.
The lake is composed of liquid sulfur at about 400 degrees Fahrenheit. The lake of all the sulfur, I'm telling you, all the sulfur's coming out, And this area has been deposited there.
Over there, yeah.
Look at that camera. You see the whole surface.
Go.
And it's rolling around because of all the gases coming out from the volcano below.
Breaking, forming.
Yeah.
Yeah, so you can see this is probably a few tens of feet here. But you can hear it in scientists' voices. Nobody ever expected to find a lake of liquid sulfur a mile, no, not a mile, but a kilometer down in the seafloor. It was quite an event. So we talked a lot about sulfides, and I also mentioned CO2, but here is another remarkable spot. You can see here these chimneys are all white, meaning this is a low temperature fluid, not a lot of metals, mostly calcium carbonate. And I keep saying sometimes you can see the bubbles go by, but remember, we're 6,000 feet down. So there are no bubbles. No bubbles. These are all top of the better side. Well, these are droplets, there we go. Those are droplets of liquid CO2. Maybe from a marble to a golf ball size. You can see them kind of, the shape is not very malleable as they're flying upwards, but no one had ever seen this anywhere before. We all know that carbon dioxide comes out of volcanoes, but in such a great magnitude as we saw in this location had never been seen before. It's pretty amazing stuff. Okay. All right, so that's all the cool stuff. Now, volcanoes and life. Okay, so what didn't we see on the seafloor and all those ecosystems, all that stuff? What was not there compared to an ecosystem on the surface of the planet? No plants. No plants at all, because we're down several miles. On the terrestrial side, everything is a photosynthetic food chain. Starts the whole thing. Leaves pick up the photons, chloroplasts do. They use the light energy. They make reduced carbon compounds like plants. The herbivores eat the plants. Carnivores eat the herbivores. And the whole cycle continues. That's what drives life on the surface of the planet is the photosynthetic food chain. Don't have that on the sea floor. We have a chemosynthetic food chain. It's powered by hydrothermal vent and the sulfide, the hydrogen sulfide, one of the most toxic gases known to humans, is coming out of the vents. And microbes live on hydrogen sulfide because it's a great energy source thermodynamically. So everything else lives off the microbes that live off the sulfides. You can see here, this is again the picture of the tube worm. The plume is all red because of hemoglobin. It's a microbes, like the hemoglobin, like you and I have, but somewhat different, not chemically different, quite different. And that's what's used to absorb all the sulfides and brings it to the all the microbes in the cavity, and the food, the worm lives on the microbes in the cavity and everything else. So we have energy, we have microbes making reduced carbon compounds, and then the carnivores eating the reduced carbon compounds. No plants, like everybody's going to do. So that's how it works on the deep sea floor. They're totally different. So people were beginning to think, well, I should back off for a second. For a long time, the earliest life seemed to be divided between bacteria, single-celled microbes with no cellular wall. Their DNAs are floating around, and then the rest of us in plants and animals, multicellular, a nucleus in the cell. But more and more, when microbes were sampled from this deep sea and other extreme environments on the planet, actually, people began to see that there was another kind of microbe that did not fit the chemistry, the biology of this at all. And they were called extremophiles, and the official name is archaea. And archaea might possibly be the first attempt at life on the planet. And the bacteria and the plants and the animals followed from the archaea and other similar bacteria. We'll never know, since we can't go back in time, but that's the prevailing theory. So, challenges for life on early Earth. The early Earth, the first billion or 2 years, was a really difficult place to live. Really difficult place. First of all, asteroids and meteors, comets were continually bombarding the planet. And that's how the planet grew. That may be how the planet got much of its water. That may be how the planet got some of its organic compounds. But living up here on the surface of the Earth, it's hard to see how anything could survive easily. I think years and years ago, the view of where life began was sort of a gentle pond somewhere, where everything is comfortable and there was plenty to eat and warm temperatures. But that isn't what the early Earth was like. And even later, a billion or so years later, about a billion years ago, the Earth went through several episodes of ice cover, and occasionally may have covered the entire planet. And, people say there might have been or scientists say there might have been a snowball Earth. So let's look at that. The clue is, not the clue, but the question is, were seafloor vents then? Were they oases of life? Were the only thing that could survive safely for billions of years might have been seafloor vents. So now I'm going to give you a little bit about the climate history of the Earth. This is a very broad stroke approach. A lot of details are being left out. I'm happy to answer any questions later on, but in general, this covers about 4 billion years of Earth's time. It's not a linear scale. You can see this is sort of expanded here for ease of seeing. You can see how the estimated temperature kind of goes up and down and up and down. Here's where the dinosaurs flourished back in the Mesozoic. All the plants were going crazy, and the dinosaurs were too. And then we started a lowering during the Pleistocene Ice Age. And of course now we're conducting an experiment to see if we can get a place where dinosaurs can live again, I think, because we're going to be raising the temperature of the planet a lot more than it has been for quite a while. So, it turns out that some recent data shows that about 3 to 4 billion years ago, the giga annua, I'm using the same terminology, just think of billions of years. 4 billion years, 4,000 million years. Plate tectonics probably began about then, and perhaps life began. Very little information, but some very telling information. When I was putting this talk together, I was going through some recent papers and things, and I ran across a couple of interesting papers. 3.5 billion years ago, some rocks were laid down, and they've been recently analyzed and recovered. And it appears that the rock chemistry would fit beautifully as an organic-rich vent fluid. And then organics in the rock, the typical, the kind you might find around vents, and they required a certain temperature form that you find about bench. So in fact, there might have been organic material and vent fluids at this time. Now, one thing about the early Earth that's also difficult, this is a graph of atmospheric oxygen in the atmosphere. A billion or 2 years ago, there was virtually no oxygen in the atmosphere because there was nothing to make oxygen. This here is called the Great Oxygenation Event, 2.5 billion years ago, where green algae appeared and they went to work making as much oxygen as they could. In almost no geologic time, they went up to roughly where we are now. These are not land plains, though. These are just like algae, okay? So still, if there's life here, this suggests life perhaps. If there's life here, how do they survive with no oxygen? They're probably living in the crust, not on, in the crust at the bottom of the seafloor, not perhaps on top of the seafloor, using all those fluids coming out. Small one. A recent paper showed that you could create oxygen back then by tectonic generation. And that means the rocks are always moving, being rubbed against one another, not always, but frequently. And that moving motion, kind of like a Boy Scout starting a fire, could recover some oxygen that's locked in those kinds of rocks and make oxygen available to the microbes that could be living on the seafloor. So now we have evidence of life, and now we have a way to get oxygen. So this looks pretty good. It's a pretty good argument for early life before there were plants and animals in the seafloor. Okay, what about the ice ball problem? The globe apparently got covered 750 to 580 million years ago, and that doesn't look good. That's before green plants. So here's how it might have happened. For reasons unknown, there might have been an extended cold period. The oceans begin freezing. The polar caps a bit large. But volcanic outgassing is still taking place, putting CO2 into the oceans. The next step is, when more and more ice gets on the planet, the reflectivity increases, and a lot of the solar radiation disappears into back to space. And there's a feedback loop, so there's more and more ice, and more ice occurs, the reflectivity grows, so less and less warming. But the volcanoes under the ice are still pumping out. And eventually, they get enough CO2 in the atmosphere, because a lot of the CO2 that comes out now from our cars goes into the ocean. But if the ocean's full of CO2, then it only goes into the atmosphere. And this may have happened there, so that now all that CO2 is going into the atmosphere and slowly but surely making a greenhouse planet. And the greenhouse gas gets hot enough to melt all the snowball effect glaciers, and then you're back to where you were to begin with, and maybe or maybe not a cycle restarts. This is not imaginary, but it's certainly not proof. It's just an idea about how this could happen and how life could survive under the snowball effect. There's life still going on because of vent-like animals living in the bottom of the sea. Okay, what about life beyond Earth? That's a really intriguing question that a lot of people have been asking for a long time. We'll start with Mars. There's no obvious water on Mars, but curiosity was there, has been there. And back in February, they sent back these pictures, and the interpretation is that these are rippled rocks shaped by waves on ancient Mars, like lakes or oceans. People think there was water on Mars 3 or 4 billion years ago, and this is some good evidence that it was possible that long ago. But now on Mars, there is a lot of water at the South Pole. There's a mile-thick layer of dust and ice, including the deep lake even, about 10 miles across, and that might be functioning as an ocean with microbes on the seafloor. So there's a possibility here, I guess, in the North Pole as well. No little green men, though. Now, what about Europa? That's the place where the Voyagers on 2001 were headed, you might recall, to put the monoliths on the moon. They were headed there. Might have been a good reason. This is a picture of, this looks like looking at the Earth from a very long distance and looking at all the tectonic plates. But either that or a bunch of icebergs in the Arctic Ocean. These are all like huge ice flows, if you will, put all together. And the crucial thing about this is it's not frozen in place. These pieces are obviously moving around, which means something must be moving below them and providing heat. They're not just stuck in place forever. So here's a picture from the Hubble spacecraft, and it's images of water plumes coming out of Europa. And here's the interpretation. They make these interpretations by flying around Europa, measuring the gravitational pull, and the electromagnetic field around. And they can say for a moon of this size, it can't be all rock. And there's probably about 60 miles of water and an ice crust. Remember, it's absolute zero out here. And because of the gravitational pull, gravitational heating from Jupiter, it's really disturbing the inner part of Europa. That's what's causing, providing the heat that makes hydrothermal vents and keeping this water unfrozen. So you have an ocean with volcanoes. Sounds like a place life can make. One more. Now we're going on Saturn, going to Enceladus. It's a smaller place. They use the same kind of information to assume that there's a nicer water crust. And I think Cassini went by and measured spectrographically measured the chemistry of these plumes and found them to have the kind of molecules that require a temperature of over 200 degrees to form. So that's a good evidence that vents might occur. Okay, so I'll close by saying, not reminding you, but I'd say when I was a young boy back in Chicago, I used to be enthralled by the summer night sky. I would go out sometimes in the evening and walk down the road, and there was a golf course near us, and I'd go down and lay on the 7th green, a short par 3 over a creek, and look up at the sky. And there were so many stars. And even then I wanted to be a scientist. And I read a lot of science fiction. And I had a fervent wish, I gave myself a wish at that time, that I would live long enough to know that there was alien life in the universe. Some kind of signal. Well, 30 years later, I'm part of a global group of researchers scouring the Earth for vent sites, looking for animals so alien, an environment so toxic that few people could ever have imagined that. And what they discovered was simple and profound, is that volcanoes, in the presence of water, can certainly sustain life, but they may even be able to form an environment that's conducive to the creation of life. Life is adaptable. Life is tenacious. Now that we see that there's volcanoes and water more common in the solar system than we thought, that suggests there are volcanoes and water in the universe more common than we thought. And I think that means life in the universe is more common than we thought. And that's, for me, that's a boyhood wish come true enough. Thank you for your attention. I enjoyed that.
Let's have some questions.
Yes, sir.
Yeah. It's one
Yeah.
year.
Actually, last night I looked at a NOAA special on the volcano in the South Pacific that created the tsunami that overtook Tonga.
Yeah, the Tonga.
Yeah, and that was,
I worked at that volcano.
oh, you did,
Yeah,
okay.
in the past. Well, luckily, I wasn't working then, but go ahead.
Well, I was just, you know, it seemed huge. I mean, it was just amazing. Could you maybe just talk a little bit about that?
Well, I think the most remarkable thing, as far as I understand about that, is how far up in the atmosphere the cloud went. More higher than I think almost any volcanic plume that has been measured. And one reason for that is that the volcano is very shallow. I can't remember the number, but hundreds of feet or so. So when it had a big eruption, since it was so close, it was a big volcano to begin with. It just put more energy in the atmosphere than any other volcano eruption. We went around for Krakatoa, which is another famous, or Pinatubo, which I think is pretty big. And there might have been some other issues, atmospheric, that I don't understand, that enhanced that eruption. But yeah, it was a spectacular thing.
Is there any volcano that big close to us?
Yeah, Mount St. Helens. Yeah, 43. Yeah, or underneath, no. There are no big volcanoes like that because we do not live on a, that's called a subduction zone, a volcanic arc. That's where, anyway, a volcanic arc. We don't have a volcanic arc in front of us. The West Pacific is full of volcanic arcs, like the Mariana Arc. Where that one was the Tonga Arc between New Zealand and Fiji. That's full of those kind of volcanoes. A lot of underwater volcanoes, but we don't have a volcanic chain. We don't have that kind of subduction zone going on here off unfortunately. The reason is the melt, when the melt goes below the other overlying plate, that plate is already inland of the continental, so its volcanoes are on land. Other places are further off, so their volcanoes are in the sea. Yes?
What can you tell us about the Yellowstone
Yeah, very good.
situation?
Yellowstone is also a volcanic hotspot. It exploded some tens of millions of years ago. I don't know the exact number. I think it covered a third or a half of the country with ash. And it is an ongoing hotspot. I wondered if someone would ask me, what about Hawaii? That's not near any plate boundary at all. How come there's a lot of volcanoes there? About a dozen places around, or 24 places around the planet are what's called hotspots. No one really knows how the dynamics work, but there's these places deep in the mantle. Magma comes up from hundreds of miles, and for many, many years, and it impinges on the surface, and it stays in the same place. Hawaii is one of those places. You can track the Hawaii Islands back thousands of miles. As the plate moves over the hotspot, one volcano after another is formed. And Yellowstone is one of those hotspots. But our continent isn't moving nearly as fast as the Pacific Ocean, as the Pacific plate. I mentioned Iceland. Iceland is one of those hotspots also. That's why you can walk around in Iceland, because there's so much magma coming up to Iceland. So there's a ridge at Iceland and a hotspot, so everything's high, and that's why you can walk around. Yellowstone, if you're planning on living another 1,000 years or so, you could be worried. But it's still, I think that they can measure uplifting of the crust, and certainly the heat flow is higher than the crust around, so that is a real hot spot, and someday, again, if humans are still around to watch it, I think something will happen there. Yeah.
Just a quick follow-up.
Yeah.
Do the prevailing winds from the west protect us somewhat in this area?
Yeah, Yellowstone goes off.
Yeah.
I'm not an atmospheric guy. My guess is yes, except that within a week or two, what goes around comes around. All the way around the globe. And maybe it'd be like a mushroom cloud, only with a mushroom cloud diameter of 1,000 miles. I don't know. But it's going to be a big, it could be a big one.
want to say first, that was a magnificent presentation.
Oh, well, thank you.
Wonderful slides.
Well, it's not my first rodeo, I will say that. And,
It's beautifully clear. You used the graphics so well to make your points. I really appreciated that.
Sure.
I was thinking, as you went along, how many things you discovered that you weren't expecting,
oh,
and how often that required autonomous vehicles and drones and things that where humans couldn't be there.
right.
And whether that means you, for example, might be particularly open to AI. That is to say, to the use of...
You get that politically loaded comment in there, right?
Well, it just seems to me like we moved in a direction
Yeah.
where if you attach intelligence to
Yeah.
those vehicles, we'll learn even more. And there's much more to learn.
Yeah, so you're talking about ships that are just going to be sailing the ocean with AI on board. And yes, yes, it's going to help, and it's dangerous too. But yes, you're right. I've been lucky enough to discover a lot of things because our mission at NOAA was to explore. I guess I can mention one. In the 80s, we were making preliminary surveys on the Huantuca Ridge looking for plumes, and all of a sudden we were raising these instruments up and down, as I said. And on the way up, we were coming up and up, and the plume hadn't gone away. It was still hundreds of meters above the bottom, and the plume was still there. We thought some of the equipment had gone bad, which often happens. And then we went down, and the same thing happened, and we finally realized that something different had happened. And we discovered inadvertently a thing called the mega plume. And that was, I think my boss coined it, clever little term, but it stuck. Anyway, what we hypothesized, and we know now, is occasionally the ridges, for reasons that are still not clear, that release 1,000,000 times more hot fluids than they might in a whole year on a given ridge section. And you never know where, you never know when. And the biggest thing about them is that they showed that those the whole system is not a steady state system of just chimneys percolating along forever. Bursts happen, and when bursts happen, things change big. It's like erosion perks along a little bit on the beach until a hurricane comes, and then in a day everything's changed. So it's sometimes really the big events which make the most difference. And we were just, damn lucky to be there that week. And over the next 15, 20 years, we discovered these things in about a dozen places around the globe. So yeah, we've been, and most of the stuff I showed you was stuff that we did not expect to see. We didn't expect to see the drops of CO2 or the exploding bubbles or a lot of the other stuff. That's exploration. It's been the best part of my career. Well, thanks very much.